Hello my friend, welcome to another video. Today I'm talking to you about threads. This is gonna be just a very simple introduction. It's not meant to be fully exhaustive, but it is enough to understand the overall ideas. So what are threads? If you open your activity monitor here, we can see all the processes that are running right in your computer in this moment. For example, OBS, which is actually the software I'm using to record my screen, VirtualBox, Google Chrome, and many other processes, right? You know pretty well that always in the background there is a lot of stuff going on inside your computer. Now, the thing that is interesting is this, threads, right? Every process has a specific number of threads. For example, look at Google Chrome. It has 45 threads. Then, of course, we have the kernel, which has many threads. But generally speaking, you can see that every stupid program has threads, right? Even Cheat Sheet, which is just this program that allows me to see all the shortcuts, has 9 threads. It is a simple process, a simple program, nonetheless, it has threads. iTerm, the terminal, has 8 threads. Well, put in a simple way, we can say that a process is composed of threads. Every process is composed of threads, even my hello world. Let's create an hello.c process. Here it comes. We have our printf program with a sleep, so we can check how this process behaves. Okay, so I'm gonna launch it. So compile, and then I'm gonna just launch in the background. As you can see, if I do ps, my program is still running, is this one. Now let's search for a.out, and here it comes. This is my hello application, and as you can see, I have 1 thread, you see? So the take-home message that I want to give you is that every process has threads. Even your hello world program has threads. Only one, the main thread. But this is it, right? Every process is composed by 1 or more threads. We decide as programmers if we need 1 or more threads. This is cool because with threads we can exploit really well multi-core chips. Threads are really powerful because they allow to exploit really well your computer, all the cores that you have available. If you split your thread of execution, your main thread of execution, into many threads, you can fit all of them in all the cores that you have available, right? This really makes the code much faster if you know what you're doing, because this, as you will see in the video, will create some quirks, will create some strange effects. I think that a practical approach is far better than just talking about an abstract point of view, right? Explaining the differences between processes and threads. I think it's not fairly useful. I'm gonna try to explain these concepts with a simple analogy and with code, which is always the best solution in my opinion. So the analogy, the parallel that we are gonna use in this video is gonna be of Starbucks, Starbucks workers. I think it's gonna make everything fairly easy to understand. So let's create a program that I call Starbucks, like that. And this program, let's say, is gonna mimic the work of 2 baristas inside a Starbucks. So let's do that. Of course, I'm gonna include standard input output, and let's start with the main function. So here I will have 2 routines that I call, I don't know, make coffee. And here I'm gonna put the name of the barista. I don't know, I'm gonna do Luca and Paolo, like that. Cool, now let's implement the function make coffee. So it's a void make coffee that takes a string that I call name. All right, let's do a simple printf. So barista is making coffee with the name. Then we're just gonna include the Unix standard for the sleep function, just to mimic the making of the coffee. Let's say 3. Okay. And then we're gonna print coffee ready. Perfect. So we have our silly function make coffee. That's it. That's our process, single threaded. Let's launch it. So compile and launch. So barista Luca is making coffee. Then we have the sleep. Coffee is ready. Paul is making coffee. The sleep. That's it. A very stupid program. Let's improve this. Let's use threads. So Starbucks threads. So the usual standard input output, unisd, and this time we have to include also the pthread.h. This, of course, is the library that allows us to create, manipulate, and leverage all the threads. I will explain while doing the thing. This time I want to create 2 threads that will act as baristas. So to do that, I have to declare this pthread type, okay? And I call this Paulo, okay? The other pthread, let's do more clear, let's do better, like barista1 and barista2. Now, to create the thread, I have to call the function pthread create. Okay, so this is the actual function to really kick in the thread. As the first input, I have actually to pass the address of this variable. Okay, so here I'm gonna pass the address of barista1. The pthread create function is gonna insert inside this variable a specific value, a specific ID for this thread. Then I have this other parameter, which is attributes. We don't really need this, so we're gonna put null. These are specific attributes for the threads, but this is sophisticated stuff we don't really need at the beginning of our journey into threads. So this third parameter, as you can see, is a pointer to a function, and this is the actual job, the actual work that the specific thread has to perform. As you can see, the function returns a void pointer, a generic pointer, and takes as an input a void pointer. But essentially, I have to implement the function as before, make coffee. Just we have a different prototype, so it's going to be void star make coffee as an input void star. And here we can say generically data, right? We can pass whatever we want to this function. Usually we use structs, because with structs we can pass a lot of data to the actual functions, but by now we don't care. Okay, the function is exactly like before. We just don't have strings. We don't need by now, so we just want to see how these threads work. Okay, let's go back to our pthread create, and here we're gonna insert the actual pointer to function. You know that to pass a pointer to function, you just need the name. You don't actually need to put an ampersand. This is just redundant. Okay, perfect. At the end, we have the actual arguments, which are nothing by now, so it's gonna be null. All right, cool. We do the same thing for the second thread, so I'm gonna copy it past and just change here to barista2. And this will effectively create my 2 threads, right? This is already a functioning program. Let's just launch it and let's see what is going to happen. So compile, launch, nothing happens. Why is that? So the issue here is simple, is that we are not waiting that our threads are concluding their specific function, their specific task, right? The main function, the main thread is going on, is creating the first thread, the second thread, and then it's going to reach the final curly brace, finishing the actual process, right? When we reach the final curly brace, the process is finished, but the threads were still working. We're still in the process of making the actual coffee. So here we can say something like that. You can say, I don't know, sleep of 5, for example. Let's try now. So let's launch again. And as you can see, this time we have the actual output. And cool enough, we have the 2 baristas that are actually preparing the coffee simultaneously, as you can see, right? We have barista preparing coffee ready. Not like before that we had like barista is making coffee, then he actually made the coffee, and then we have the other barista that is starting to do its stuff later, right? Now we have only 2 baristas, but I'll let you imagine when we have, I don't know, 100 baristas, the difference. Let's go back to the code. Of course, this is an hackish way of doing things with the sleep. We shall use the pthread functions. Indeed, in this case, the function on end is going to be join, pthread join. So this is a function that is taking the actual pthread value, the pthread ID. So I have barista1 and barista2, and here we have another value that by now we are not going to take into consideration, maybe later. Basically, with this argument, we can get back this return value from the function. Anyway, so let's call this join function to barista1 and barista2. The join function simply means, hey, let's just wait that actually the threads finish their execution. So the main thread is going to wait the termination of the actual threads. It's basically like the wait function for processes, right? When the father is waiting for its child to finish. Let's launch now. So compile, and as you can see, it works exactly the same. This is a multi-threaded program. Let's make a sleep year of 20 and let's watch again our process. I have 3 threads. Of course, I have my main thread and the 2 threads that I've created. Okay, so this is a very silly, stupid multi-threaded program. That's it. Now let's go into the extremes. Let's do baristas, which is going to be an array of threads. Let's say an array of, I don't know, 500 baristas. And then we are just going to make a loop. This time I just pass as an input baristas plus I. Baristas plus I, because here we have to pass a pointer, and you know that an array name is going to decay into a pointer. So this is just pointer arithmetic. Every time I'm going to pass the actual address of the right cell in the array. And then the function is the same. Of course, I have to do a for loop also for the join. So this time is going to be baristas in position I, and here again I'm just going to use null. Let's try to launch again this process. So compile and launch. Boom. Look how many baristas we have. More than the actual kernel, you see? Our test has more threads than the kernel. With a single threaded process, you cannot have so many baristas running simultaneously, right? Here I have all the baristas that launch the make coffee function, all of them kinda together, because of course this is not real parallelism. I cannot have 500 cores. I cannot have all the threads really running simultaneously. I will have a lot of concurrency. This is what we have, but a real parallelism is impossible. At a certain level, I don't have all the cores for all the threads. So this is probably a good important point. There is a difference between concurrency and parallelism. I pledge you to check by yourself. With processes, I cannot have all of this, right? I can only have one thread that is running on one function that we have to sleep. So I will have one barista making a coffee and sleep, making coffee, sleep, making coffee, sleep. So that's it. So of course, here pthread create is gonna give you back a value, which is different from 0 is something went wrong. So here you should do something like that. If pthread creates and returns a positive value, like you exit, something like that, okay? You just search pthread create and you will get this. If successful, pthread create function will return 0, otherwise a number will be returned. Here I just wanted to show you all the actual values of all the threads. So we're gonna make another for loop. So we are gonna just print the identifier for the actual thread, okay? And launch. As you can see, all the threads have a specific number. This is the actual number that we need to really identify the actual thread that is running. It's like a badge, right? We have our barista with a specific badge. That's it. So given that we have this power to model a Starbucks shop in our computer thanks to thread, let's do that. For us, threads are like the workers inside the Starbucks. The Starbucks is actually the process. I have my worker and I have my boss. Let's see what we have to do. So the boss wants that everything has to be served and reported. So every drink that has been served has to be reported into a specific ledger. So I have my waiter that goes to read the specific value inside the ledger. So this is like a read operation. In our computer is a load operation. Basically, we're taking the value from the memory and bringing into the CPU. Then we are gonna actually serve the clients, right? We're gonna serve with the 2 coffees, and then the waiter is gonna go back and is gonna write the data updated, right? So this is a write operation or a store. We have the value processed by the CPU, and now we can put it back into the memory. Easy vanilla, easy peasy, cool. This is a single thread process. We have only one waiter and everything works. Now let's try this again with 2 waiters. This is gonna be already probably messier, but nonetheless, let's have a try. So again, my waiter is gonna read the value is going to save inside his memory. This value is going to serve the clients 2 coffees, goes back, update the ledger. Now we have 2 drinks. The other waiter is going to do the same, read the value, serve the clients, go back, update the value to 4. Cool, everything works, right? Amazing. Well, not really. This was just dumb luck. The thing is that we have only 2 threads and we have a very simple operation, which is composed of 3 steps, right? We have to read the value, serve the clients, write back the value. 3 steps. So it's a very silly operation made up of 3 atomical parts. So let's rewatch the animation and let's check if something gets messy. Okay, we have the waiter that is reading the value. Then is gonna go to serve the clients. But this time, the second waiter is gonna go to the ledger and read the value. Both waiters have the 0 value in their mind, right? So the first one is serving the clients, then goes back and is gonna update the value, right? It's gonna update to 2. Then the other waiter is finishing to serve the clients, goes back, and here what happens, my friend? Well, here we don't have an update to 4, but we still have an update to 2, right? Because the waiter has in his mind the value 0. You have to keep in mind that these threads are not talking. These waiters are not talking. They don't know each other. They just work in this place, they see a value, and they have to update that value by themselves. We go back and the boss now is angry, right? Because we have in the ledger only 2 drinks. So what we shall do, we have to fix this problem. This problem is called a race condition. Why a race condition? Well, because we have 2 threads, 2 waiters that are racing toward a shared data, in this case, a common ledger. So we need a trick to avoid these problems. What shall we do? Well, we can have like a special lock that is blocking the access to this ledger, the shared resource. So only the waiter that has the key to open this lock can write into this ledger. This is going to take more time, right? But at least we are sure that the code is correct, then the data is not going to be wrong. So let's try to implement that. We're going to apply a specific lock to the shared data. So we have the waiter that is going to the ledger, is going to read the value, and then he's going to lock the access to the actual ledger. Cool. Then the waiter is going to serve the clients. And I have the other waiter that is reaching the ledger, but this time he cannot access because it is locked. He cannot write there. He cannot read. He cannot do anything. This waiter has to wait. It has to wait indeed. It has to go to sleep until it can read the ledger again. So it goes back. It just waits. The other waiter does its business, is going to serve the clients, goes back, is going to write the new values that is going to be true, and then is going to open the lock. Boom. And goes back to his place. Cool. So this time the waiter that was waiting can read the actual value, right? Because the lock is open. So it's going to read the value, lock the value again, and it's going to do its business. So now, if the other waiter wants to, again, go to the ledger and read, it will find a locked ledger. No problem. So the waiter that is serving can be totally sure that the ledger is not gonna be modified while he is serving, he is speaking with the clients. No problem. So the waiter does its business, goes back, updates the value, unlock the lock, and everything is fine. Everything works, right? And our boss is a genius. He has cracked the code. Of course, this will take more time to serve the clients because every time I have one waiter that is waiting to access the ledger. It's a trade-off, right? As you can see. So let's do a program now that I call race condition. The thing is that we have to implement what we saw in the animation in actual code. Let's do that. So the actual boilerplate, I'm going to include all the stuff. Now we have the ledger, right? Let's create a ledger, which is a global variable, which is a shared resource. Every waiter can see this. So let's do it very big. I'm gonna include standard integer so I can use unsigned int 64 like that. Type ledger. Now let's create all the threads. I'm gonna go very fast. And let's implement the actual function updates. So I have void star, right? Void star, update ledger, and as an input again, void star data. And here I simply say ledger plus 1 plus equal 1. Okay, a very silly operation, and return null. So every waiter is thus increasing by 1 the actual global variable ledger. Here at the bottom, I just print the result. So all right, let's compile and launch. And we have 96. 96. How is that possible? Of course, this is a global variable, so it's gonna automatically be assigned the value 0, right? Let's do anyway, and let's retry. 100 this time. This is correct. Let's retry. Let's retry. Let's retry. 99. I can do while true. Okay. I'm launching the process many times. As you can see, I have the value 100 something every time it changes. It is not all the time 100. How is it possible? What is going on? If I do 1000 threads, I still have the same problem. As you can see, every time I have different values. As the number increases, I have mistakes that are gonna be bigger and bigger. So you understand the problem here, right? We have actually 1000 waiters that are accessing the same resources. And this creates this mess, right? Everyone is just accessing at the wrong time the ledger. To solve this problem, we have to actually implement a lock when we access the shared resource. So we have to put a lock here, right? We have to put a lock. And here we can simply release the lock. How can we do that in code? Well, we can do that with mutexes. These are structures that allow to stop a specific thread to execute a specific code, which is called the critical section. In our case, the critical section is actually accessing the shared source. So now we have to create this lock, right? We're gonna do that globally, so everyone can access with no problem. And to do that, we are gonna do pthread mutex type, and this is gonna be the ledger lock. We can initialize this struct in two ways. There is the static initialization, which is the best option for our specific case, but there is also the function init that works in this fashion. For example, in the main, I can call mutex init, and I pass the actual parameters here. For example, the address of the ledger lock, and the other one is gonna be just a null. So this is a way to initialize the struct, and this will work. So by now we're gonna do that, even though the best way when we have something like that would be pthread, if I can, pthread mutex initializer. These are essentially two ways, this code and this code, to achieve the same thing, but of course there are some subtleties, there are some differences, but never mind, that's the same thing. We're gonna go with the static initialization. You can look up by yourself, it's very easy to find the difference. Okay, now we're ready to go. Here we just have to add the code, which is pthread mutex lock. I'm gonna pass a pointer to the ledger lock, and then after the waiter has done its business, it's gonna unlock for the following thread, for the following waiter, right? The function is specular, which is unlock. Very simple. And we pass ledger lock. That's it. So my friend, this is actually the code from my representation, from my animation, right? Let's try to launch. Risk condition. Let's launch again many times. And as you can see, all these times I get 1000, 1000, 1000, 1000. I don't have any more the problem that was arising with race conditions. Of course, every time I have to unlock, because otherwise we get into a stuck. We're gonna be stuck. The lock is gonna be forever closed. And that's it. We're stuck. And the code, as you can see, cannot move on. So this, in my opinion, is a good picture of why mutexes are cool. They actually encapsulate some piece of code, which in our case is the update of the ledger, making it safe, making it atomic. When we say atomic, we imply that this is a piece of code that is gonna execute it atomically if you want. This is not actually what happens because we still have the scheduler, but once a waiter has the lock, nobody else can enter. Okay, so it's like the waiter goes there, takes the lock, close the lock, do its business, goes back, opens again the lock. So I think that with this image and with the animation, you have a good picture of why mutexes are useful when we use a multi-thread. Now maybe you still have a doubt. So what is the actual difference between a process and a thread? I will try to explain again with my analogy with Starbucks. A process again is just the full Starbucks itself. It's like the entire Starbucks shop. We can have Starbucks China, Starbucks Hawaii, Starbucks Africa. It's the actual cafe place. The mission of the Starbucks is all the same. It's the same process. Sell overpriced caffeine to all the people. The same process, okay? They are actually the same, but they are different. They are in different places. Threads are actually the workers which are inside the specific cafe shop, inside the specific cafe shop in China, in Africa, and so forth. You got the point. So the thing that you really have to keep in mind when we talk about threads and processes is that threads share the same memory. Indeed, threads share the same place. They work all in the same place. On the contrary, processes are different entities, right? I have a process which is in China and the other process which is in Africa. They don't share anything. They are just copies of themselves, you see? So race conditions, this strange phenomena that you just saw, happens only with threads, happens inside the actual process. So we can say that race conditions are intra-processes phenomena, not inter-processes. So race conditions happens because we share the same memory space, and this happens with threads. So a waiter in process A cannot really mess up with the data in the process B, which is in Africa. Totally different places. Now I will show you in code. Include stdio.h. Again, we have a ledger. Cool. Then we have the main function, of course. And this time we're going to use the fork. So basically we are going to split the process. We're going to have a child and a father. So I'm going to include unistd. Okay, let's do that. So I'm going to have a pit type pit. And here I'm going to save the return value coming from the fork function. So it's going to pit is equal to fork. We know that if the value of the pit is equal to 0, we are inside the child, right? Else we are the father. So the child is gonna increase the ledger by 42. Let's say ledger plus equal 42. And then I'm gonna print the value of the ledger from child. Okay, the father is gonna do the same. Is gonna increment the ledger by 42. Is gonna wait for its baby, right? We have to wait that the child is gonna finish. It's fairly similar to the join function, right, for threads. And then it's just gonna print the same thing, this time from the father. Okay, that's it. So basically that's it. I have my process, my main process that is gonna split into a child and the father, and both are gonna update the ledger by 42. So what can I expect from this code to get a ledger of 84 or 42? Let's watch out. So I compile and launch. As you can see, I get from both 42. Of course, because the ledger lives inside a specific process, a specific cafe. So I just want you to focalize on this image because I think it's self-explanatory. Processes are in different places in memory. We don't have this problem of race conditions. On the contrary, when we are in the same building and we have a lot of threads of workers running simultaneously, well, that's when a lot of mess can kick in. All right, that's it for this video. This is just a very simple, I hope, introduction to threads. I hopefully will make more videos about this topic, which is big and not very simple. Threads are a pain in the you-know-where. All right, thank you for watching, my friend. Enjoy.